There is an idea or hypothesis about volumes of gas. It suggests that any gas in a fixed volume, at a fixed temperature and pressure, can only hold a fixed number of particles. In other words, the same volume of any other gas, under the same conditions of temperature and pressure, must contain the same number of particles. By comparing the mass of each volume, we can find the relative mass of individual gas particles. How small are these individual gas particles? And could they in fact be atoms? If so, we found a way of comparing the mass of atoms in a chemical reaction. In actual experiments, we can get one gas to react with another gas to form a third gas. It seems logical that a particle of this third gas must be made up of not one, but at least two atoms. One hydrogen atom and one chlorine atom. But perhaps there are other kinds of gas particles made up of only one atom. What about hydrogen and chlorine? Is there some logical way of explaining how these two gases might be made up of a single atom particle? Perhaps we can get a clue from carefully observing how volumes of gas combine together in different reactions. Fortunately, the French scientist Guy Lussac did the work for us more than 200 years ago. From his observations, he found that two volumes of hydrogen always combine with one volume of oxygen to form two volumes of water vapor. One volume of hydrogen combines with one volume of chlorine to form two volumes of hydrogen chloride. Three volumes of hydrogen combine with one volume of nitrogen to form two volumes of ammonia. From these observations and others, Guy Lussac proposed the law of combining volumes. This law states that gases always combine in ratios of small whole numbers. Could at least some of these gas volumes be composed of single atom particles? Let's explore one reaction more closely. We don't want to lose sight of our universal particle container idea. If several gas volumes are the same size, they must contain the same number of particles. So let's see how this hypothesis might affect the behavior of the smallest particles of gas. What we would like to do is preserve the hypothesis and at the same time demonstrate that at least some of the particles are composed of only a single atom. Imagine some faraway planet where different kinds of creatures behave like atoms. These very civilized creatures all wear very civilized bags. Under the right conditions, these creatures get together to make whoopee. And here's how it works. They get into the same bag. There's one important rule, though. One bag gets only one seat. No matter how many creatures in a bag, the rule never changes. one bag gets only one seat. Now compare these tuxedos to our gas particle bags and the creatures to atoms. Let's imagine each gas particle also has its own seat. In other words, a little space all of its own. Imagine that this space is a kind of universal particle container. One space contains only one particle. Any other space the same size also contains only a single particle. And it doesn't matter whether the particle is made up of two atoms, or only one, or many. What we have now is a direct relationship between a volume and a particle. In a gas reaction, we can think of either a number of equal volumes combining or a number of single particles combining. Suppose we now increase the particles in a reaction by the same number. We increase the number of the same size spaces. Since in each case they are the same size and the same number, then in each case they add up to the same larger volume. We've increased the number of particles, but the relationship between our original single particle and a single volume hasn't changed, even though the volume is now larger. The relationship stays the same whether each volume contains 4 particles or 4 billion, as long as the numbers in each are the same. So, if we predict a reaction that combines single particles, we can expect to observe in the laboratory a matching equal volume for each particle. That's what the universal particle container idea suggests. We want to hold on to this idea, but we also want to open up these particle bags and hopefully show that some particles are only single atoms. In theory, the simplest possible gas reaction is this. A single atom particle of hydrogen combines with a single atom particle of chlorine to produce a 2-atom particle of hydrogen chloride. Matching a volume to each particle, we would expect to see this in the lab. 1 volume of hydrogen combining with 1 volume of chlorine to produce 1 volume of hydrogen chloride. If there are single atom particles of gas, this is what the universal particle container idea predicts. Now, what did Gay-Lussac observe? 1 volume of hydrogen combines with 1 volume of chlorine to produce 2 volumes of hydrogen chloride. Oh, something is wrong here. Is there any way we can alter our thinking about atoms and particles? And can the universal particle container idea still explain Gay-Lussac's observations?